for chapter 15. So we will talk about the human movement in a fluid medium, and that's a very important topic in biomechanics, but it's not fluid mechanics, it's biomechanics of the entire body in a fluid. And that's different from what you will be learning in the, what they call the biotransport class. That's different from that. So we're going to talk about how composition and flow characteristics of fluid affect fluid forces. And here's the thing. Can you name all the forces that we learned about so far in engineering? So we're dealing about, it's biomechanics, so we're dealing about forces, correct? So can you name the forces that we learned about so far? Yes, no, maybe so. Remember we talked about reaction forces? Remember these reaction forces? When you have things on, so let's say if I have a truss and that truss is sitting on the corners and objects, those are called reaction forces, right? They're the forces that limit the movement of an object. And then we talked about something called external forces. So if you're pushing on something, that's an external force. And then we talked about something called internal forces inside the truss. When you cut the truss, there's internal forces, right? And then we talked about friction forces. Remember? So all these types of forces. So the mechanics or biomechanics is the study of forces, correct? Now, we would like to learn about new forces in fluids that actually are important when you do the analysis, static analysis or dynamic analysis. Does that make sense? And these forces are going to be the forces caused by fluids or an object inside fluid. Then, so drag is a force, right, guys? Drag is a force. And so what is drag? And how to identify the components of drag. Then lift is a force from fluids. That's another force. So we'd like to look at this force and the characteristics of these forces. So that's what we're going to be doing. So from this chapter, what I want you to take is that we would like to learn about all the types of forces in fluids or caused by fluids, and then add those to your analysis. So you're skilled now in analyzing object in static and dynamic equilibrium, but we need to add as many forces as we can. All right, so let's start. So before we go into the forces, we'd like to talk about liquids. So can you define a liquid as a state of matter? So how would you define a liquid? It takes the shape of its container. So and that's something called a state of a matter. So the state of a matter, you have, how many states do we have? Liquid, gas, solid, right? So when you define it, you need to define things that can characterize those. So if you want to do that, we'll say, well, it's a mobile, condensed phase. Why did I say mobile? Mobile because it flows, right? Condensed because it's not gases, right? It's one entity. And then it's a phase. So that's a phase of a matter. And if you recall from material science, that's important when you define those. Whose volume is fixed under conditions of constant temperature and pressure. And also, shape is usually determined by the container it fills. So that's how we define actually the liquid. One more thing, the liquid, it does not prevent other objects from penetrating it. So we have the state of micromobility of that phase of the matter, characterized by inability of the weak bulk cohesive forces. So the molecules, they have a cohesive force, but it's weak. That does not prevent the penetration force of any macroscopic object directed to any cell. Make sense? And macro means big, a big object. So that's the definition of it. Now, change of state. So the state. So you heard me talked about phase. Do you recall? Can you remember what is the definition of a phase, a matter? A phase. So if I say that I have a phase of a material, so let's say this plastic, is it one phase or multiple phases? It's multiple phases because I have this material inside. So a phase is a homogeneous material that you cannot have borders that can distinct different physical properties. Does that make sense? But here, this is solid, but this is softer. So that's multiple phases. Now, I would like to talk about state. So consider a system of a matter composed of a homogeneous. That's important. Homogeneous means it's all the same. A distribution of atoms and repetitive atoms. Do you remember crystallinity of metals? Repeated blocks. So if they're repeated, that's homogeneous. So it's a homogeneous state with no boundaries separating it into parts identifiable by differences in physical property. That's the meaning of a state. or a homogeneous state. Now, here's the thing. The conversion of this system from one state of matter to another, if I'm changing a material from liquid to gas, that's change of state, right? You can't say that unless the material is 100% homogeneous. So you can say, well, the conversion of this system from one state to another by the manipulation of the external variables is called a change of state. So the change of state, you can't say that the material is having a change of state unless it's homogeneous and it's one phase. The external variables can be temperature, pressure, mechanicals. So if you take water, you increase the temperature, it becomes vapor, and that's a change of matter. As long as the water is purified water, not, let's say, salt water. For that, it has to be homogeneous. Now, an ambiguity arises if they call the phase transition. So phase transition is not change of state. And we're going to talk about that. And I think you learned about this in material science when you have alloys, when you talked about alloys. So that's called phase transition. We're not going to deal with that now. Now, have you seen this graph before? You probably saw this. If you increase the energy and then the solid to liquid to gas, that's increasing the interparticle separation. And you have between the two states, so between solid and liquid, there is a change in the potential energy. If you increase energy, the material becomes liquid. Increase the energy more, it becomes gas. So you've seen this probably before in material science. You've seen also the TP diagram, the pressure, temperature, solid, liquid, and gas, right? If you increase the temperature and the pressure stays the same, you have the gas state. If you increase the temperature and increase the pressure, your gas will become liquid. Reduce the temperature and reduce the pressure, you're going to get a solid material. Now, why is this important? If you are dealing with polymers or any biomaterial, you need to identify these graphs for that material. And especially that polymers, we are mixing a lot of polymers. We're creating new polymers. So you need to have, if you work as an engineer for a company that is creating polymers, you need to be able to assess their TP diagram and also their potential energy change of state, how they're changing from one state to another state. So that's very important. But that's that's material science. But I wanted you to know that what is the definition of liquid and what are the things that we care about when we deal with liquid. Now, going to our chapter, the first thing, what is a fluid? So we talked about liquid, right? So liquids and fluids, they're different. So fluids is a substance that flows or continuously deforms when acted on by shear force. That's the definition of fluid. Now, liquids and gases, both of them are actually fluids. Does that make sense? Both of gases and liquids are fluids. So we need to be careful when we use the terminologies. So when an airplane is, flying, it's actually flying in a fluid, in a gas. And that's a distinction people need to understand as we move on. Now, more about fluids. Air and water are fluids that commonly exert forces on the human body. And that's what we want to learn. What are the forces that can actually affect the human body or movement, but coming from fluid environment? And for example, the ability to control the action of fluid forces differentiate elite from average swimmers. Understanding these forces can actually make a big difference when people are actually swimming. And I'll show you what do I mean by that. Because you need to be able to identify your center of gravity and center of volume. You know the center of volume? We talked about center of gravity, center of mass. There's something called center of volume. Now the center of volume is something we need to identify because that is affecting the forces generated by fluids or liquid. Now let me show you what I mean by that. So here, before we start with the liquids, we have to make sure that we are on the same page when it comes to something called relative velocity, right? Now, so let's say someone is on a train and the train is moving and there is on one direction let's say from right to left, and there's another fellow riding a bicycle from left to right, and we would like to find the relative velocity of the biker relative to the train. So how would you do that? Do you remember how we do this physics problem? So yes, first of all, you need to identify your reference direction, positive, where is that direction? And then, but here's the thing. What is the thing that you subtract? If I'm trying to find the velocity of the biker relative to the train, which one I'm subtracting? If I would like to find the relative velocity of a biker relative to the train, which one I'm subtracting? You subtract the train velocity. So you subtract the latter from the former. If you're doing the relative velocity of a biker to the train, it's the biker velocity minus the train velocity. That's how you do it, right? That's very important, guys, because that's when we do the biomechanics problems, an example, that comes important for us. So the velocity of a body with respect to the velocity of something else, such as surrounding fluid. So here's an example. So let's look at this. I have this biker and I have the wind, right? When I'm seeing the apparent velocity of the biker is 15 meters per second. So the velocity of the cycle, so the biker is 15, that's the apparent, and I have a wind of 5. The velocity of the cycle relative to the wind is how much? So he's moving to the left, apparently 15, but there is 5 meters per second wind pushing back, but I'm seeing 15. So how much he's actually driving, to overcome the 5 from the wind. So this one, the 15, is the apparent velocity, which means that he has to do 20 to compensate for the 5 coming on the other direction to go 15. And that's important, actually. Now, on the other side, if the cycle velocity is 15, the apparent is 15, and he is feeling 5 on the back, how much is he driving? It's 10. You need to add them, right? So 10 plus 5, that's 15. So his velocity relative to the wind is 10. Okay, a question. So let me give you a piece of paper and see if you can solve this. Okay, so let's take a couple of minutes and see if you can find this. So we have a sailboat is traveling at an absolute speed of 3 meters per second. Again, so now absolute, that's not relative. That's absolute. It's not apparent. Now, against the 0.5 meters per second current with a 6 meters per second tailwind, what is the velocity of the current with respect to the boat, and what is the velocity of the wind with respect to the boat? First, make sure that you have a notation of the direction. Then, if you are doing, let's say, the current with respect to the boat is the velocity of the current minus the velocity of the boat. That's very important. But first of all, you need to start with setting up a notation for the directions, which is positive and which is negative. Let me see. I'm going to assume going to the right positive, and then let's see how we're going to do it. Okay, we got solutions. So let's do it together. Tell me, what do you want me to do? Who wants to help me? So if you would like to find the velocity, so let's do it here. So the velocity of the current with respect to the boat, right? So it's the velocity of the current minus the velocity of the boat. Do we agree? Now, if you have the current, where is the current? The current is going left, so that's going to be negative. So if I said minus 0.5 minus the current of the boat is going to the right, which is 3, right? That's positive, minus 3. So that's going to be minus 3.5 meters per second, or you can say that this is 3.5 meters per second. In which direction? In the direction of the current, right? Or against the direction of the boat, because it's with respect to the boat, right? So you say 3.5 against direction of the boat, because we would like to do this with respect to the boat, right? Does that make sense? Or you can say that's 3.5 going the other way, left. I'm fine. As long as you have a notation for me to follow, I'm good with that. Okay, how about the other one? So what do you have for the velocity of the wind with respect to the boat? So it's velocity of the wind with respect to the boat, correct? Now, that is going to be velocity of the wind minus the velocity of the boat. And wind is going right, that's positive, that's 6, minus the boat 3, that's also positive. So that's going to end up with 3 meters per second in the same direction of the boat. Or you say that's going to the right. Does it make sense? Make sure that first you have your direction notation, which one is positive and negative. And then you make sure that if it's the boat with respect to the wind, it's the boat minus the wind. And that's how you calculate that relative velocity. A lot of people actually get this wrong when they measure the relative velocities, because they don't put the directions correct, or the signs correct. Are we good? Yeah, but whenever you're putting something with respect to it, I will say in that direction. So I will say the velocity of the wind with respect to the boat is 3 meters per second in the direction of the boat. So that's good. And so that's checks, right? 3.5 to the left, that's a solution. V current minus V boat, and that's negative 3.5 to the left. And the wind with respect to the boat, the velocity of the wind minus the velocity of the boat, and it has 6 minus 3, and that's 3 to the right direction. Yeah, so I like always to have in the opposite direction of the boat, or in the boat, you know, the direction of the boat, especially if you ask in which, relative to what. That's important. We good? Alrighty. So now we will talk about the nature of fluids. Remember, the goal is to identify the forces, but we need to look at the nature of fluids in order to be able to see how they are actually creating forces. So we have something called laminar flow, and the laminar flow is characterized by parallel lines of the liquid. It's how it's flowing. And so the laminar flow is characterized by a smooth, parallel layers of the fluid, you know, even you're passing through them or they're passing through the object. Now, the opposite to the laminar flow, now here's the thing, with laminar flow, do you think you are getting a lot of resistance or low resistance? It's low resistance because it's laminar flow. Now, once we have something called turbulent flow, now then we have, it's a turbulent flow that's characterized by a mixing of the adjacent fluid layers. And now there are a couple of things happening here. First of all, we have discontinuity in the flow of the fluid, correct? Between the front and the back. Make sense? That's one. So you're having now turbulence instead of laminar flow. The second thing, the pressure in the front is way much higher than the pressure in the back. And this pressure difference creates forces. That's a problem. Now, imagine we are in the bloodstream and you have a clot, and the clot, or not a clot, let's say we have, this is a blood vessel, blood is flowing, laminar flow, everybody's happy, we're good. Now, let's say we have a blood vessel and I have cholesterol, right? A buildup of cholesterol. Now, what's going to happen to the blood here? It's going to flow this way, and then it will move, and then we'll do turbulence backward. Do you know what the turbulence go? This is force. So there is force in the blood caused by the turbulence. What's going to happen is this turbulence is going to break the platelets at the end, here, at this point. When the platelets break, everything in the platelets will go out. And now I have a big problem of, like, I think that there's a bleeding, and it's going to create a clot. And that clot will form here, and then this clot is going to travel in the bloodstream. Once it goes to the brain with the small blood vessels, you have a stroke immediately. So the problem with cholesterol buildup in the blood vessels, it's not that the cholesterol itself, but it's what it's doing to the flow, the turbulence flow, and then fooling the platelets that we have bleeding for it to create a clot, and that clot will travel to the brain, and then you have a problem. Another problem for turbulence flow in the blood. In the blood vessels. See here in our body, we have a blood vessel that comes from the heart, and then it goes this way. Right, guys, you see that? So there's a blood vessel comes here and then goes this way. Now, anytime we have like this, a junction of the blood, because of the turbulence at this junction, we create something called an aneurysm. So what happens is that your blood vessel creates a bubble in that junction, and then the blood will continuously go in, do more turbulence and go out, and then gets bigger. And then the blood goes in, do more turbulence and go out, and it gets bigger until it ruptures. And we have a bleeding, in the internal bleeding, and then death because of these aneurysms. So the blood flow, the laminar and the turbulent flows, because our cells are, adaptive, and they react to the mechanical environment outside because of the forces, they can have very big clinical consequences on those, and that's what we need to understand and how to look at it. Does that make sense? Now again, go back. Laminar flow, we're good. Turbulence flow. If you have turbulence flow, it means that you have difference in pressure and you have force that is generating a lot of turbulence after that turbulence. Does that make sense? How we look at that? Now on the microscopic scale and macroscopic scale, it's the same thing. That's what we are generating. We good with these two characteristics? Okay. Now, and remember that the reason why we have a force is because of the change in the pressure in the front and the back. We have something called, let's talk about fluids. Again, I'm trying to get some, general information, but I'm trying to put a context around it in what we're doing. So if I would like to look at the properties of the fluid, things that we usually measure. We have something called density, right? You know the density? It's mass per unit volume. And what is the unit of the density? Kilogram per meter cube, because it's mass per unit volume, correct? So the unit of the density is kilogram per meter cube. Now, we have something called specific weight. Now, specific weight is just like the density, but instead of mass, we use weight. So weight per unit volume is the unit weight. So what is that unit? What's the unit of the specific weight? It's newtons per kilogram per meter cube, right? Does that make sense? Because newton is the unit of a weight. Now, we have viscosity. Now, viscosity is the internal resistance of a fluid to flow. So when you look at this one is Newton meter square multiplied by second, because you have the resistance to flow, and it depends on the force, it depends on the area, and it's flowing, it's seconds. So it's Pascal second. What's Pascal? Newton per meter, it's stress, right? It's stress multiplied by time. That is actual resistance. Does that make sense with how we're looking at that? So these three things, these three quantities are something very important we need to identify for any fluid before actually start looking into understanding the mechanics of that, objects moving into that fluid. Does that make sense? Okay, this is a table that shows you some values. Remember, we have fluids, right? And fluids include gases and liquids. Now, we have density, kilogram per meter cube. Do you agree? Then we have a specific weight. It's Newton per meter. So that's wrong, actually. It should be the big N per meter cube. It's Newton per meter cube. Now, the last one, viscosity. It's Newton second per meter square. And if you look at the values, so air has a density of 1.2, water has a density of 998, seawater is 1026. That's the density. Ethyl alcohol, 799. Am I pronouncing it correctly? Ethyl alcohol. And then you have mercury. Look how big that is, 13,000. It's very dense, and that's why we're using it in thermometers, temperatures. Now, specific weights, those are the values, and then you have viscosity. Which one do you think is the larger the viscosity, the harder the fluid flow? So air, very small, mercury 0.0015. This is a very, very, very large value actually for a viscosity. Now here's the thing, here's a cool thing for biomedical engineers. We do a lot of blood tests, and people can look at the concentration of fats or minerals in the blood, but few people do actually the viscosity test. If someone is diabetic, how much do you think it's larger viscosity or lower viscosity? Diabetic people, their blood should be larger. There's a lot of glucose, just like honey. It's a lot of glucose in the blood, and that means the flow is hard, which means the heart is pumping a lot. So they are actually hurting their hearts and their kidneys at the same time with diabetes because of the viscosity of the blood. So that's another test that people would probably hire you to do viscosity testing of liquids. And now, here's the thing. Someone is taking aspirin. Do you think that their blood viscosity is higher or low? Very low, because it's a blood thinner, right? The aspirin. So that's another thing. All right, let's talk. So we talked about liquids and reviewed a couple of concepts, and we did an example about the relativity. Now, here's the thing. Let's start with force. The first force that is related to fluids is called the buoyancy force. And this force is a fluid force, and it's always vertically act upwards on the subject in the water. Do you see this swimmer? Now here's the thing, guys. The buoyancy force is related to the volume. Weight is related to the center of mass. So the buoyancy force is always acting on the center of the volume, and the weight is always acting on the center of mass. We need to understand this. So look at this swimmer here. See this point? That's the center of volume, and that's where the buoyancy force acting. And then we have a center of gravity or center of mass. That's where the weight is acting. With what that is. Now, in order to be floating, you need to make sure that you are actually, the buoyant force is equal to the weight, but also they should be on the same line so that you don't have tilt. So for this subject, what do you think is happening here? If the two forces are equal, do you remember the couple moment? You have two things pushing this way. So what's happening is either tilting this way or tilting that way. It's usually the other way, this way, the subject. The only way the subject will float if the center of volume is the same, aligned with the center of weight. Do you remember I told you that elite swimmers know how to use the forces in the fluids? That's one of them. They know exactly where their center of volume is and try to put it with the center of weight or mass. You need to have them aligned to be able to float. Now, if they're not aligned, you need to start moving. You need to add other forces. So when we are swimming, remember we push ourselves. So you're adding another force, external force, to balance the two. A good question. So Archimedes' principle said that here's the key thing. The magnitude of the buoyant force, it's a force. I need to find its magnitude. So the magnitude of that force acting on a given body is equal to the weight of the fluid displaced by the body. And that's how we calculate it. So what I'm doing here, I'm relating force to the volume and weight of the body. So there's a formula to calculate this, and I'm going to show it to you. So the point at which the buoyant force acts is the subject center of volume or the center of buoyancy. That's very important to keep in mind. Now, the calculations. According to the Archimedes principle, the buoyant force equal the volume displaced multiplied by gamma. And gamma here, you have F is the buoyant force, V is the displayed fluid volume, and gamma is the fluid specific weight. What is the specific weight? It's the weight per unit volume, right? So that is Newton per meter cube. That's specific weight, right? That's not density, that's specific weight. It's Newton per meter cube. So if you would like to find the buoyant force, you multiply the volume by the fluid specific weight, and each fluid has a specific weight. It's the weight divided by the volume that is occupying. And that's how you calculate this force. Remember, we're in a biomechanics class. We need to look at the forces and the moments. So we'd like to understand what are the forces that can be generated by. Okay, so what determines whether a body floats or sinks? Well, according to that principle of equilibrium, floating occurs when the buoyant force is greater than or equal to the body weight, right? Because it's pushing upward, and the weight is pushing downward. If the pushing up is larger, then the body will float. And then you have sinking occurs when the body weight is greater than the buoyant force, and the body will sink down. Okay, the equation of the sum of the vertical forces must equal to 0 to float in a motionless position. And that's the example that I showed you. If there is a distance between the buoyant force, the center of volume, and the center of gravity, we will have torque created, a couple moment on the swimmer by body weight that acts at the center of the gravity of buoyant force that acts at the center of the volume. And you will end up with something like the rotation, right? Because you have two forces with a distance. Now, if the torque is eliminated when the center of gravity and the center of volume are vertically aligned. Okay, let's do an example. So here's an example. I want you to try it for, let's say, 3-4 minutes. When holding a large quantity of inspired air in the lung, a 22 kilogram girl has a body volume of 0.025 meter cube. Can she float in a fresh water with a specific weight that is 9,810 newtons per meter cube? Given her body volume, how much could she weigh and still be able to float? So let's take a couple of minutes. Yeah, for this problem, make sure that you find out the buoyant force first, and then look at the weight and see if the buoyant force is larger or smaller. And if it's larger, the body will float. If it's smaller, the body is not going to float. And how much the weight should be for the girl to float, actually. The formula? Yeah, so so the FB, I'm writing here. So FB equals V, the volume, multiplied by that gamma. Yeah, so here, if you want to do the multiplication, the volume is 0.025. Why did I use this? Because it's they said that the volume of the body, right? The entire body. And that's how much water will be displaced if she got into the water. Now, remember, you need to make sure that it's meter cube, right? So that the units are multiplied correctly. So that's 0.025, and then you multiply it with the specific weight that is 9,810. So, and what's going to happen is that this is in Newton per meter cube, and that's meter cube. They will go together, and you'll end up with the multiplication in newtons. How much is that? 245. Point what? 0.25. I will just put a 3 significant figure, 245. So that's how much the buoyant force is. Now, how much the weight of the girl? So the weight of the girl should be 22 multiplied by 9.81. How much is that? So do 216, and what is the unit? Newton, right? Now here's the thing: the buoyant force is pushing upward, right? Always, and the girl is 216, which is bigger. It's the 245, so she will always be floating. Make sense? Because the force up is larger than force down. Now, how much she should weigh in kilograms and she can still be floating? 25 kilograms. So what happened is she has to be at least that much before she sink, right? So that's 245. So that's the weight equals kilograms multiplied by 9.81. So you take 245 divided by 9.81, and that's how much. This is how much mass the girl will get. That we good? So that is how you look at the buoyancy force and how you use it. And if you check the solution here, we multiplied the volume by the specific weight. That's what we're getting. The weight of the girl, 22 multiplied by 9.81. That's what we get. Yes, she's going to float because her weight is smaller than the buoyant force pushing up, and she needs to be at least, equal to the buoyant force in order to be able to float. If her weight is larger, then she will sink, and you can get by dividing by 9.81, you'll get how much mass the girl will. Are we good? So so the first force is buoyant force. The second force is called drag. So that's another force, a liquid, force that we need to look at. So let's say you have a wind tunnel, right? And you're putting, let's say, something that is flat. See how much you at the beginning you have, and it's moving this way. You will have laminar flow here, and then because of that flat plate, you will have turbulence. Now this is going to create a large drag force. Now here's the thing: where is the object moving? What direction of the object? This way, correct? The drag force is pushing backward in the opposite direction. The buoyant force was pushing up all the time. We need to make sure that we understand this. So, and if it's a sphere, you have a smaller drag force. If it's a sphere with a tail at the end, that will be a smaller drag force. And if you have an indentation in the beginning and the backward, you have even less drag. Now, if you look at the airplane, see this airplane, the wings, we don't have, like this wing, cylindrical, rectangular wings, because this is going to create a huge amount of turbulence out. That's why we try to have some sort of curvature at the beginning and the tail at the end to reduce the drag as much as possible, to control it, not just you reduce it, to control it. Does that make sense with how to look at that? Now let's understand how drag is a force, just like buoyant force, caused by the dynamic action of the fluid that acts in the direction of the free stream fluid flow, and it's always a resistance force that tends to slow the motion of a body moving into a fluid all the time. It's trying to slow the movement, the drag force. Now, we have multiple types of drag. And we're going to learn about them. One of the drags is called interference drag, and we have a shock drag, we have a resistance drag, and I'm going to explain those to you because each one of them has a different formula and different things that can control that drag for us. So let's start with this. The first thing, and the drag, the reason why we have the wings this way is that we would like to control the drag by changing the orientation of the wing, not by the structure of the wing. Does that make sense? I would like to control it by changing the orientation, not the structure of the wing, to dictate my drag. So when an airplane is taking off, which of those is the orientation of the wings? When it's taking off, it's this one, because you want to reduce drag. You don't want to have resistance. You want to reduce the resistance. Now, when the plane is landing, if you look at the wings in the back, when they fly, it goes inward, and when it goes down, it comes out and become like this to create that drag for you, to do that thing, the dragging. Yeah, it's a cool thing to look at the aerospace dynamics, how we're going to look at that. But it's now getting, well known. It's nothing, new in that field. Okay, now here's the thing. We have a formula for the drag force, just like the buoyance. The buoyance force was the volume multiplied by the specific weight. Do we agree? For the drag force, it is the multiplication of the coefficient of drag, which is CD, which is a unitless number that serves as the index of the amount of drag a body can generate. So depending on the structure of the body, we will have a different coefficient of drag. So if you have a body like this compared to a body like this, you have different coefficients of drags. Does that make sense? It's a geometrical quantity depending on the body itself. And then you have the rho, which is the fluid density. And what is the unit of density? Kilograms per meter cube. And AP is the projected area of the body, of the surface area of the body perpendicular to the fluid. So AP, which one is larger? Let me show it this way. Which area is larger here? And that's where the flow is. So AP, the perpendicular to the fluid flow, this one is larger. So the larger area means larger FD, which means that a larger resistance. Does that make sense? How we look at that? And now V is the relative velocity of the body with respect to the fluid. That's where it comes. It's very important. It's the relative velocity of the body with respect to the fluid. So it's the velocity of the body minus the velocity of the fluid. Does that make sense? After you have a stand where the positive and negative is. So the relative velocity of the body minus the relative velocity of the fluid, that's your relative velocity of fluid that you add into the drag force. And that's why we learned about it. Does that make sense? Good? Alrighty. Now, here's the thing. Skater, right? Ice skater. And so the ice skater, because of what they're wearing and how they actually, the body is actually moving, they have a CD of 0.26. The coefficient of drag. Now, if it's a biker, the coefficient of drag is larger because we have a larger area right now that the biker is actually covering. Now, a parachute is 1.2. So it's a geometrical quantity that dictates the value of that thing. The larger that value, the coefficient of drag, the larger the resistance force. And remember, the resistance force is just like the friction force. It's in the opposite direction of the motion. Does that make sense? Good. Okay. The larger the coefficient of drag, the larger the drag force, the resistance force. Okay. Now, skin friction is a drag force. So skin friction is a drag force. And I'm not talking about friction when a car is moving on the road. I'm talking about friction through a fluid, right? So resistance derived from friction between adjacent layers of fluid near body moving through the fluid. So here's the thing. Look at this picture. If I have this as, let's say, the airplane wing, and you have the laminar flow of the air around it, if it's not 100% smooth, if you look all of them, make sure that they're smooth. If they're not smooth, see these small turbulences that are taking place close by the surface? That is going to create a drag, actually, which is a resistance force. So the disturbances or the turbulences close to the surface creates a drag. And that's substantial, actually, especially when you increase the speed. So that's called surface drag or skin friction or viscous drag, because it depends on the viscosity as well as of the fluid or the air around. Which one do you think is more viscous, a dry air or moisture? A moisture, because you're going to create shear force between the two objects. So that's important. So are we good with what surface drag is? I told you there's a lot of types of drag. So that's called the surface drag. And that's why actually swimmers nowadays, they cover the whole body with the suit, because the skin actually can create a lot of friction because it's not smooth. And that's why dolphins are faster than other fish, because their skin is very, very smooth. Does that make sense? It makes a big difference. And I think I will double check, but I remember that the skin friction for dolphins is way smaller than sharks. That's why it's hard for sharks actually to catch a dolphin, because of that friction. Nature. Okay, so laminar flow and turbulence flow. So if you have this plate moving in a liquid or a flow, a liquid, and it's passing through it. At the beginning, you would have laminar boundaries, and then these boundaries, they start to go away from each other, and then after a while, toward the end, we get this turbulence. The fluid boundary layer for a thin flat plate shown from a side view, laminar boundaries layer gradually become thicker as flow progresses along the plate, and then we'll end up with the turbulence. Right. So that's very important. And now, where do you think this is also important in biomedical application? Do you know stents? Stents, we put stents to open the blood. So these stents actually sometimes they can generate turbulence if they're not designed well, and if they stayed a long time and then they build cholesterol around them. It's a big mess. So that's why I like to have degradable stents with drugs that they can actually release heparin and make sure that no clotting is taking place around those. Okay, so let me just finish this. What affect the magnitude of the skin friction or the skin drag? Increase proportionally with increase of the velocity, you'll have more friction. Increase of the surface area, you have also more friction. And roughness of the body surface, increase the friction. And the viscosity of the fluid. The higher the viscosity, the larger the resistance of them, generated the drag resistance. Drag. Are we good? So I will stop here today, and then we'll continue on Wednesday. And Friday we will do the MATLAB. So I know that I've received 2 of them, but I'm still missing one of your timestamps. Yeah. Okay. So before we go, is there any questions here? We good? Yes, I will go to it one.